you guys in that crucial week, the better off I think everybody is at this point. Okay. So this week we're going to talk about Bode plots. And unfortunately in the book, they don't put much emphasis on it. In the book, it's an appendix. So we're going to have to shift to the back of the book and go to Appendix D and E. Okay. So we're going to start this week in Appendix D and E. Just give you a little background. Where are we at now? Remember, we talked about Laplace transformation this whole time. We learned circuit analysis. We learned how to do circuit stuff. And we figured out transfer functions. And pretty much we realized that given a poles and zeros in a circuit, you could kind of see behavior of the circuit, whether it's infinite impedance, zero impedance, infinite voltage, zero voltage. You kind of get an idea of how the circuit works based on different frequencies, right? Remember, at the end of the day, all your S's, you could plug in a JW in it and actually set W equal to a specific frequency, 1,000 radians a second, right? And you can actually get a hard number out of it, like 147 volts, 147 negative 53 volts or something, right? That's the idea of this circuit analysis. You get a general form of a circuit, right? But then you want to ask yourself at different frequencies, what happens to a circuit? This is very important because, I'm going to skip ahead just a tad to the chapter 14, but a circuit that we build typically does not just work for one frequency unless we're in a power system. If we build a cell phone or an antenna, we expect different frequencies to get put into the circuit, right? I mean, like if you have a radio and you have an antenna, right? Different signals are going to come to the antenna, so the radio is going to get all different frequency levels, right? And then you have to tune the frequency to whatever 103.5 that whatever station's around here, right? And so the idea here is you could build a circuit. I mean, a radio is nothing but electronic circuit to tune into 103.5, right? And then shove out any of the other stations. That's kind of how radios work. So a lot of circuit analysis is involved with tuning into frequencies, splitting up frequencies, changing them sometimes, right? And so with that being said, we have to kind of think of how can we show a circuit that can change in frequency and we can observe it easily, right? Rather than doing the hard calculations every single time, right? And that's what a Bode plot is. A Bode plot is just a graphical representation of frequency domain, right? Remember, we always had time domain graphs, all right? Time domain graph, right? And you see something do this, right? And this is maybe 100 volts, and this is 0 volts, right? You could tell as time goes on, right, that this circuit is going to crap out, right? It's charged at the beginning and then it kind of just tanks itself. So maybe it was capacitor charged up and then it dissipated, okay? So graphically at 1 second, 2 seconds, 3 seconds, we could figure out what's going on. Well, because we're doing Laplace transformations, we're more in the frequency domain. What stops us from asking, well, what happens when we put different frequencies in here, right? Maybe this is 103.5 megahertz, right? So really technically actually we write F right here, not W, right? And that radio was tuned into that. So what do you think the output of the radio is going to be? It's going to be dead for all this. Let me use a different color. It will most likely be dead for most of the bandwidth and then spike up at 103.5 megahertz because that's what you tune the radio into, right? And this output voltage will be relatively high compared to the rest of it, right? And that's just you tuning into that frequency on the radio. So we can make a circuit to do this, right? That's the preparation, that's the circuit analysis and the synthesis part. But how do we graphically show this? That's what we want to see, right? We want to see that, we either, let 103.5 megahertz flow through, or another example would be in stereo systems, right? Subwoofers tend to have low frequency devices. You don't put high frequency sound waves through a subwoofer because it's not going to be able to push anything, right? So how do you do that? Well, if you have a subwoofer, you want to make sure that you only let the low frequency stuff through. So what you'll do is you'll put a up to maybe, I don't know, 150 hertz, right? Anything below, you're going to want to let the voltage through and let the subwoofer work, right? Anything at a high frequency, you don't want it to operate, right? So that, again, we can make a circuit, a filter to do this, right? Another thing people like to do is they like to filter out high frequency noise, right? You know, one thing I always show people, I guess I always heritage my video game background is you guys remember old school PS1 controllers? Note that, see these controllers, they don't have, it's a straight cord. If you remember the older ones, they had this little round plastic piece in front of it, right? Like right here. You see that little cylindrical plastic piece? What is, anybody have a clue what that thing is, what that's for? Right? I mean, like, how come some of them, this one doesn't have it, right? This one has it right there. No, that one doesn't have it, right? This one has it right there, right? What it is it's a filter, right? You could actually take this off, by the way, and throw it in the garbage if you want to, but it filters out unwanted noise, right? So sometimes the older controllers, because the cable is long, and if you put it near other sensitive electronics, I mean, like if you actually put this near a microwave or your old school cordless phone, it would mess up the signal. It really would, right? So you have to put a filter to filter out the high frequency noise, so the normal signal that it wants will go through. That's right, VGA cables have that, right? These things, right? These are, again, filters, right? I don't think DVI has them, right? Because some of them do, some of them don't, right? Because once you get to DVI and HDMI and all that, it's a digital signal. A digital signal doesn't really need that, right? Some of them do, some of them don't, right? It's an old school analog signals that really needed them, right? Because analog signals can be really messed up by noise, right? When you go down to your digitalized signals, we have a lot of error checking algorithms that we can rebuild a waveform otherwise, but old school analog didn't have that, okay? So again, that's why you had your PlayStation control is actually much more complex control than all your other ones if you ever took it apart, right? So they needed that little filter, otherwise the control will be unresponsive sometimes, okay? So anyway, this is just a more real life example of what are filters, why are we even talking about circuit analysis? We're talking about building those little cylindrical devices on cables to make everything work correctly, right? So that's what Bode plots are for. Bode plots are graphing a circuit to see what the frequency spectrum, how it operates in the frequency spectrum. What happens at low frequency, what happens at high frequency, right? You know, if you have a frequency graph, and let's say the circuit does this, what does that tell you, right? Well, there's a middle area that it'll let frequency through, right? And the outside is going to kill them, right? This is a bandpass filter, okay? If you see a circuit do this, what does that mean? It's it lets high frequencies through, right? If you see a circuit do this, it's a low frequency, right? So depending on how you build your circuit, you could do any of that, right? But we need to graphically show what is the characteristics of the circuit, where does it actually turn on, where does it turn off, right? We need a little mathematical detail here. And that's what Bode plots are. It's a graphical representation of the frequency domain and how the circuit operates. And it ties into Laplace transformations, right? We do the whole idea is we have a circuit, we do Laplace transformations, figure out a transfer function. A transfer function has poles and zeros, and with the poles and zeros, we could figure out how the circuit is going to behave in terms of frequency. That's the big picture of what we're trying to do. Now, before we get to that, we need to talk about a specific unit that's used in Bode's plots as well. It's called the decibel. We've heard this somewhere in our lives, dBs, right? Something to do with sound, typically in a speaker, right? So we're gonna have to give a little history lesson where that came from, okay? So the idea is, long time ago, we built telephones. Telephones were the old crank ones. You had to crank it up to get some power through it, and then you send the signal through. It physically went through a cable. The cable could be long, it could be 10, 20 miles, right? The longer the cable, the more power loss you're gonna have, right? But what happens if you're in San Francisco, right? You wanna call to Washington. So, or actually, let's even make it this funnier, right? So let's do local to us. So we're in the classroom, right? Let's say we want to call San Francisco University. We would then pick up the phone and get routed to CSUS University's phone system, right? Then this would get routed outside to the phone network, right? Then the phone network would get routed to San Francisco State. And then that's going to get routed to the other room over there, okay? So, you know, if you ever thought about telecoms, telecommunication is just one, when you want to call your friend, it has to bounce around through different systems. It's not a direct connection from you to your friend like a shortwave radio or a walkie-talkie, right? You have to go through the telephone network, right? And the one I drew here, this is hardwire, right? I mean, you could do wireless as well, where you can be bouncing between cell phone towers, okay? But the question is, let's say I had 100, you know, I was talking and my power going through this was 100 watts, okay? Now, every time I go through between one area to another here, we're gonna have a power loss, right? So let's say this is only 95% efficient, right? So efficiency is 95% for that one, okay? Then over here, this efficiency is only 80%. Let's call this 90% as well, right? Or let's do 85, okay? Between this other phone network to this other San Francisco State, this is also, and you know, these two right here, they could be long distance. We're talking a couple hundred miles. This is 85%, right? And this last one, let's call this 90%, okay? So my question to you at the end of the day is, how much power ends up being in this room? How would you calculate that? Can we think about it maybe in opposite terms of 5% power loss here, 15% power loss here, 15% power loss here, and 10% power loss here? Can we just add them up? 5, 15, 15, 10. So it's 5, 5, 5, 45% power loss. All right. You can't. You have to actually recalculate this every single time. It gets a really big pain in the butt, right? And show you the big pain in the butt. Let's do it. Okay. So obviously the first one's easy, right? So let's do green. This is 95 watts. It's right here. But now we got to take 85% of 95, not 100. Okay. So let's get a calculator out. So 85, 0.85 times 95. Okay. We're at 80.75 watts. And then we're going to take another 85% hit. This is going to be 68.64 watts. And then we're going to take another 0.9 loss. So it's going to be a 61.77 watts. Okay. So as you can see, you have to recalculate this every time you go through a network, right? And this is only 5 things. I mean, if you look at a real telephone network, I mean, you got a cable from, I mean, if you want to be accurate, you have to talk about you have losses. So let's say the phone itself, we're not including that. The second it gets out the phone, you have a cable from you to the telephone pole or power line pole. Then you have to go down the street to the either the substation or the telephone box in front of your neighborhood. Then that has to be routed to one of the more major telephone networks. Then that goes to whatever telephone municipal they have here in Sacramento. I don't know, I don't have a landline, right? And then that has to get rerouted on the national telephone network that could be routed through different cities, right? And then that goes back down through the same wires and pipes all the way down to another person's telephone, okay? So we got 20 different stops, right? So the idea is here, you're right, you have to multiply percentages. We could do this really easy with a calculator right now, right? But back in the day, we didn't have calculators when phones were invented, right? So they said, well, I don't want to do this multiplication all the time. This is terrible, right? Wouldn't it be a much easier way to add all these percentages up, right? I mean, I could do that. If I have a 5% power loss here, right? If I have 5%, 15%, 15%, 10%, I can add these all together and get an easy number, right? So how can we do this mathematically, right? Again, we didn't have a calculator back then, right? So it's kind of, this is what they're talking about right here. You have 3 systems. You got the efficiency through each one, or in this case, the gain, right? I want to have a total input versus output with all 3 of these gains put together, and you got to multiply them through, right? Now, mathematicians came in and said, well, there is a way you could split multiplications into additions. There is a way. You have to take the log, right? Log says anything multiplied together can be split into separate additions. So if you take a log, God dang it, base 10 of this and all this, you can actually split them up into each individual logs added together, right? So that way we can just add them together and get a final answer instead of doing multiplication over and over and over again, right? And that's the idea of where the decibel came from. It's using this log function to split up the gains so it could be independently looked at and then added together. Now, the one problem, so and Bell came from Alexander Graham Bell, because that group thought about it. I'm sorry, no, that's wrong. Alexander Graham Bell was the he invented the phone. So that group of people back in the day, they wanted to quantify the power of the phone, and they chose this unit of Bell representing log base 10 of this ratio. Okay. Now, real quick, they decided to start putting this into action, and they realized that this Bell was way too big. It was way too strong of a number, and they were getting numbers like 0.01 or 0.5 every single time, right? And they're like, I don't like dealing with decimals. So they said, well, let's just divide this up by 10. So instead, let's call this a decibel, right? Where decibel is 10 log of P out over P in, okay? Which is 1/10 of a bell, right? And to this day, we use dB, right? dB stands for decibel, right? You can't technically use just bell, but you're going to shift the decimal point to the left one time, okay? So pretty much stick with dBs because that's what people are used to, right? Now, when we talk about circuit analysis, how does that work? Well, let's zoom in a little bit, right? You have the circuit on the right-hand side. You got your input power, you got P in, you got P out, right? You got I in, I out, V in, V out. You can even think of R in and R out, right? So to make this easy, we're going to say the input resistance equals output resistance, right? And let's quantify you know, what's the ratio between P in and P out? Well, we have that already, sorry. But what if I want, what about V in versus V out? Is it the same? Or I in versus I out? Is it the same? Right? Because sometimes we talk about power, but sometimes we want to talk about voltages. What if I want to measure, I have 50 volts in, what voltage do I get out? I don't want power, I want voltages, right? Well, is it as simple as just, you know, square rooting the power and dividing by the resistor, or is it something a little more, right? And so the idea is they look at this equation, they say, well, P out equals V out squared over RL, P in equals V in squared over RL, right? The RLs cancels because they're the same. And you got V out over V in squared, right? And the reason why is because it's always P equals V squared over R, right? Because we're squaring it, the square has to come with us, okay? So in the end of the day here, we got two, we have to look at V out or V in ratio is a square term. It's not just linear, okay? Same thing for current, right? Now, how does that translate into decibels? That's a big question, right? So here, if you remember, we had 10 log base 10 of P in, of P out versus P in, right? But we wanted to replace it, we want to stick in V out over V in instead. And we tried. And what we got was, erasing this, V in over V out squared, and I got to put like a second set of brackets like this. Okay. Now, what are the rules with log? When you have a variable, if you have something inside the log and then you put an exponential, you can always take the exponential out and put it in front as a multiplication. Okay, and that's the rules of log. Okay. And so that's what they did, is they got rid of the square term, put it in front, and that's where we get 20 log 10 of V out over V in. Okay. So basically, anytime you're dealing with voltages, your dB scale was going to be 20 log base 10 V out over V in. When you're dealing with power, it's going to be 10 log base 10 of P out versus P in. And to be honest, there's a lot of engineers hate this. It adds in a bunch of confusion, right? Because you have to specify, are we talking about voltage or power? Because we need to know, do we need to do 20 log or 10 log? Okay. For the most part, electrical engineers has to use 20 log 10 for circuit analysis, almost exclusively, right? So if you look at, if you're talking about voltages, V out or V in, you should expect the dB scale to be 20 log 10, not 10 log 10, okay? But if you are calculating power directly, it should be 10 log, okay? So in the end of the day, this 20 log 10, this is very important. Now, how does this, how do we use this? Let's say we had a circuit and, you know, let's just make it real easy. We have a source, right? And let's say, I don't want to get too much into details, but let's say we had an amplifier circuit, right? So we have an op amp in here. It amplifies the circuit, right? If our input voltage was 10 volts and output voltage is, let's say 100, right? So we amplified this, right? We have 100 volts coming out, V out, V in. Well, what's my gain? We call it straight gain, or your ratio, is equal to just 100 over 10, V out over V in, right? So your straight ratio is 10. But if you want to do it in dB, what is that going to be? Well, we got to do calculations, right? Coming here, we have 20 log 10 of, what's our gain? V out over V in is 100 over 10, right? So this is 20 log 10 of 10. So what is that going to equal to? What's a hard number? That's 20, right? You got to remember how log works. Log base 10 of 10 means you have to think, this answer is you take 10, right, to the x equals this 10 right here. And you got to figure out what x is. In this case, x is 1, right? Because it's just multiplying by itself, right? 10 to 1 is equal to 10. So then this is 20 times 1, which is 20. Okay. What if we change this real quick? You know, let me play around with logs real quick. What if I change this to 1K? How would that change everything? Well, this would not be 110 anymore, it would be 100, right? And then this will change. So we got to go back down here. So now we're asking, what's log base 10 of 100? So how do you figure out this x right here? Well, to get 100 from 10, you have to put it to the power of 2, right? So you come over here, now it's going to be 20 times 2, which is 40 dB. Okay, so that's how you use a log scale. All right. Any questions about this? You know, you might have forgot. Yeah, you might not have seen logs in a long time, since like middle school or something. So I want to go over it. Okay. Let's go the opposite way. What happens if this is 1? Right? So what's 1 over 10? So instead of being 100, we detuned the circuit, right? So this is 1 volt. So 1 volt over 10, right? This is 0.1. What's log base 10 of 0.1? Well, or we could write this 1 over 10. So in this case, it has to be -1. Okay, so we're going to put a -1 right here, and this will be -20 dB. Okay, so basically the rule of thumb is, if you see a negative dB, that means your circuit is attenuating or losing power voltage, right? A gain of 1 is equal to 0 dB. A positive dB means we get a positive gain in the circuit. This ratio up here is greater than 1 if you have a positive dB. If you have a negative dB, that ratio is less than 1. So you're losing voltage. Okay. You know, it might be worth saying, okay, right? Because I did have people get confused on this before. What if the input and output's the same, meaning we didn't change the circuit? It was the gain was equal to 1. So you have 10 volts in, 10 volts out, you have a gain of 1, right? This is a 1. How do you make this happen? 10 to the what equals 1? There's only one way this happens, right? You can make this equal to 0, right? 10 to the 0 is equal to 1 every time. So right here, you put a 0, 0 dB. So 0 dB means we're not changing the circuit. We're not increasing the voltage, nor are we decreasing it. We're just passing it through. Okay. So does everybody understand dBs? Like, you know, the log stuff is critical in understanding, you know, what's a high dB and what's a low dB, right? I mean, it's, for example, if I have my amplifier, I said it's 60 dB, is that a lot or a little? Right? Or what about -40 dB, right? Sorry. Is that a lot or a little, right? Once you get used to log scales, you could, you know, it'll come a little more second nature to you. So it just shows you, this is some common pairings you're going to see. When your ratio is equal to 1, you have 0 dB, right? When your ratio is equal to 2, you're going to have 6 dB. If it's 1.4 and 1, this is 1 over square root 3, square root 2, sorry. That's 3 dB, right? Now, because we're using 20 log base 10, every time we move up a dB of 20, we're going to increase our ratio by a factor of 10. So notice that 20 dB is 10, 40 dB is 100, 60 is 1,000, right? 80 is 10K, 100 is 100K, and 120 dB is 1 million. So you can see as you going from 40 to 60 is a huge leap. 60 to 80 is ginormous. You're going to blow up your equipment most likely. Okay. Same thing for negative. Okay. If you put a negative 40 dB, this is 1 divided. Put a negative 60, this is 1 divided. This is milli. You put negative here, this is 0.1 milli. Right? Like so. Okay. So when you play, you know, if you have a surround sound system or a stereo system, you have a big knob, you'll normally see that the numbers be like negative 40 dB, and you can put it to negative 20 dB and all that. And the sound volume will change, right? Most likely 0 dB is going to be pretty loud because that means it's not, the speaker system is not changing anything. And so the speaker system itself is usually, there's X amount of power it pushes through. It's probably pretty loud for all your speakers at 0 dB. If you ever put a deposit 20 dB, you're making the sound 10x better or louder. If you put a negative 20 dB from 0, you're lowering 10x. If you put a negative 40 dB, you're lowering it by 100. And typically anything past negative 40 dB in most stereo systems, you're not going to hear anything. If you ever put a negative 60 dB, I mean, the system's not going to push anything out because that's 1,000 times lower than what you put in. Okay. So let's say you put in, you know, you had 100 volts come in. If you do negative 60 dB, you're only pushing 0.1 volt coming out. And most likely that's not even going to turn the speaker on. That's why negatives, when you play your amplifiers, somewhere between negative 40 and negative 60 dB, you're not going to hear anything. Okay. So, is there any question about the dB stuff? The majority of the time you're going to see it in everyday life is audio systems, right? Because that's, you have an amplifier. Amplifier is nothing more than a giant op amp that you control. And typically, again, the dB scale is what the audio industry has accepted, and we used it as the de facto unit for gain. Okay. Other industries don't use dBs nearly as much. Like communications, they don't really use dB, right? Maybe telephone companies probably still do, right? But I don't know if I heard it in Ethernet. Now I think about it. I don't know. It's been a while since I had to do network administration. So anyway, I mean, that's pretty much about the dB scale and where the decibels come from. Is there any questions on that? Or yeah, SNR is always in dB, but I'm just talking about the straight, you know, voltage in versus voltage out and line loss. I don't know if they use dB scale for line loss. They might. Like I said, I haven't checked into this since 10 years ago because I used to be a network admin. When I was in college and grad school, I worked in IT for 5 or 6 years, and I had to deal with a bunch of crap I just haven't seen in a while. Right? Oh, you know, I'm gonna make the hipsters mad, but I don't care. Right? Right? You ever seen the SNR to record players? Right? You like a turntable has an SNR of 50 dB and all that stuff, right? So as a signal to noise ratio in the end of the day is how good of the signal you get versus the noise it accumulates. So for example, if we get 100 volts out, and 1 volt is noise, and 100 volts is the signal, our SNR is 100 to 1, or in dB scale, it's going to be 40 dB, right? 40 dB is 100 to 1, right? Now, a record player from the 50s and 60s and 70s, vinyls, typically have between, I've seen crappy as 30 to 50 dB, right? That's not that good. If you got a 20 dB SNR, that's a 10 to 1 ratio. That means 10% is noise. So when you're hearing that scratchiness that people love, you're like, I love the scratchiness of vinyl records. I mean, that's literally noise you're listening to. That's not the music, right? And the reason why it's noise, because you're using an analog needle on an analog piece of vinyl with little dips in it, right? So there's going to be a lot of mechanical vibrations, okay? So it's this, even 40 dB, 1% noise is pretty bad, okay? Now, thankfully, society, or most of society, I would say, we have graduated from vinyls and went to CDs, right? Have you ever wondered why we never went past CDs in terms of music? I don't know if anybody collects music. We never went past CDs in terms of technology and, you know, getting better quality CDs for audio collections. It's because the SNR audio is insane. It's like 100, right? I don't know if we'll say exactly, but right, then 98 to 100 dB for a CD player. I mean, dude, 100 dB, if we go back to our library, is 10 to the 5th, right? That means if we have 100 volts input, we're getting 0.01 volt noise. That's nothing, right? You're not going to hear it. The human ear probably can't even hear that small of a noise difference. So 100 dB is crystal clear, and unless the humans make their ears magically better through evolution, we're not going to need more than CD players, okay? So I think they said, they did a lot of tests. I want to say, I think about 80 dB is when people can tell. Like the best ears in humans have, they give them samples of music. At 80 dB, the humans can't tell any more noise, okay? But I've had, you know, I have friends, and, you know, friends are cool and all, but, you know, when they want to start arguing with me, and I'm an electrical engineer, and they argue to death that vinyls have better sound quality than CD players, and I just look at them like, no. I mean, you go ahead and you smoke all your hipster vinyl. I tell him what he's doing. The reason why he thinks that is because he's taking the vinyls and he's melting them in the kitchen and sniffing the plastic, right? That's why he thinks that. But he didn't like that too much. Yeah, normal vinyls. Is the top end ones are 60, 70, right? 50 is what you're typically looking at. And come on, I mean, like, let's think about it. 50 dB to 100 dB. I mean, that's a big difference, and you're going to hear that, right? So, and true, dude, I've had to argue to death with some people about this, and they put them side by side, and they're like, listen to the difference. I'm like, look, dude, your ears ain't that cool. You cannot compare these two devices of human ears. We need to get a actual meter, a dB meter, and put them next to each other and measure the SNR, right? You can do that. There's SNRs. You get a speaker that will output a specific tone, and the SNR meter will read that tone into it, and then it's going to record what comes out of the speaker from the vinyl record, and it's going to compare it to, and it's going to give you SNR measurement. That's literally what dB meters are used for, right? In an experimental environment, of course, right? You don't have the dog in the background yapping about it, okay? And that they did that, and they calculated some vinyls have 50 to 60 dB, and CDs have 100. And I mean, to me, I thought that was case closed. I mean, 60 versus 100. How can you argue against numbers? I realized you can argue against anything, man. Right? The guy, he doesn't believe in dB. right? He said, well, maybe lower dB is better. I'm like, wait, no, right? So anyway, right? You know, if you want to listen to vinyl records because you like the scratchiness and you like the noise, that's cool. Just admit that. Just say it. I like scratchiness. Okay. You know, don't say that I like vinyls because they're better. That's completely wrong from an engineering standpoint, right? Doesn't CD? Well, I always thought true CD music is uncompressed, right? Isn't that the whole point? I mean, I'm not a music expert, but if you directly rip a file off a CD, each song is like 15 megabytes or something, and that's uncompressed, right? But then when you compress an MP3, that's when you're losing stuff, right? I personally, MP3 suck. I know they're small, but they suck because anytime you compress a file, you're losing quality. I'm like, duh, right? FLAC is pretty good. FLAC is probably like the de facto standard of good quality right now. But I mean, if you really want perfect, you know, actual audio, you have to get actual CD rips, straight up. At least that's what my thinking is. Again, I'm not a communications engineer, so don't, you know, plaster me in the wall and shoot me with nails because I said that. Okay. All right. So sorry. Let's go. It's kind of engineering related, but I always like to talk about that, right? Because we're talking about DB stuff. No, I mean, it's true. Like I said, there's nothing wrong with collecting it, right? But when you start arguing that it's better than current technology and that we should bring back records because records were better than CDs, I mean, you're just flat wrong at this point, right? It's like I have friends who argue that we need to bring back carburetors instead of fuel injection. I'm like, are you insane? Right? Have you ever driven a car that has a carburetor? That thing is a piece of crap, right? So, but you know, you always have people argue that stuff, man. Okay, right? Again, it is amazing how strong nostalgia is. It's almost frightening sometimes, right? Okay. I think vinyl just feels cool. Yeah, I mean, like I said, there's nothing wrong. If you want to hold your vinyls in your arms and go sleep with it at night, hey, more power to you. All right. Well, we'll get you some. Okay. All right. So let's go ahead and start talking about Bode plots. Right. So remember, the idea is we talk about dB scale because we want to, instead of multiply gains together, let's add gains together so we could calculate it really easy. Well, that comes down to circuit analysis. If you remember, it's on exam and everything, you always had something like S plus 5, right, times S plus 10, and maybe an S here divided by S plus 14, right, on top. Now, that was your equation of the circuit, your transfer function, right? Well, we could, it's not that hard to look at an individual part and analyze, right? I misspelled analyze, right? You can analyze S plus 14. If I want to do that immediately, what it means is this is a 0 at 14, right? Negative 14 is negative 0 to be exact. And this 14 is critical because this is where the circuit stops operating. It flattens out to 0, right? But then the question is, what are these doing as well? Because they're multiplied in. So it's kind of, you could analyze individual ones easily, but when they're multiplied all together, it may get a little more convoluted, right? So the idea here is, again, with the log part, we could split these up into individual cases, well, 1 case, 2 case, 3 case, 4 case, figure out how each one works individually, and then add them all together. Because we don't have to multiply, we don't have to do convolution, we don't have to do all that really, really complex, FIFO stuff and all that crap, right? We just adding is 10 times easier than multiplying. I'm sure everybody in the world can agree to that. So let's use the simple stuff first, okay? Now, so coming over here, a typical transfer function from a circuit, you will see we'll have some K values and some poles and zeros. For example, this might be 100 S plus 10 divided by S times S plus 50, right? Okay, so we got some K's, some Z's, and some poles and all that good stuff, right? And so the idea here is we have a 0 at 10. So meaning if we put the negative 10 in here, we're going to cancel out, right? Same thing for the pole. We got a negative P1 at negative 50 and a P2 at 0. And if you really want to put a negative like that, sure, okay, right? Now, we can go ahead and inject a JW7S, right? So S, this is your generic variable to work with. But when I want to put a specific frequency, let's say, what's my circuit going to look like when I put W equals 1,000? You need to replace every S with a JW and then put 1,000 in there and start getting hard numbers, okay? So S is generic mathematical part, where JW is more of this frequency-based function, which is what we want as electrical engineers, okay? So every S gets replaced by a JW, like so, right? And now what you want to do, and we'll have CY later, you want to take every 0 and pole. So we have a JW plus Z1. And you want to get a common denominator or a common numerator out, right? What we want to do here is we want to get a Z1 out. So what we're going to do as a trick, we're going to multiply Z1 times JW divided by Z1 plus Z1. Okay. We could take a Z1 out and we're going to have a Z1 over JW divided by Z plus 1. Okay. So that's the operation we're going to do, where all your Z1s right here gets pulled out, and then the JW plus Z1 gets replaced with 1 plus JW over Z1. And the reason why they do this is you always want to compare your frequency to your Z1, right? So let's say Z1 was 100 and I got a JW, right? Well, in this form, it's easy to note that, well, when I want my zero to start working, I just got to plug in a W equals 100 right here, and the hundreds will cancel out, okay? So that's why they like this form, is you can immediately, maybe up at the top right here, it could get a little convoluted, not so obvious what Z1s we need. But when you get down here, all you have to do is just look at the division pairs, like this one and this one, and you immediately know where your Z1s and your P1s are, okay? Just remember, you have to take them all out. So this Z1 got replaced out here. This P1 right here got replaced out here as well, okay? And this is called your standard form, by the way, okay? Any questions on that so far? We're just doing a little mathematical rearrangement. Excuse me. Now, remember, we have imaginary numbers everywhere, okay? So because we have 1 plus JW over P1, right? And let's say these are all, let's say this is 1 plus JW over 100. And then we put W equal 50, for example. This is going to be 1 plus J 0.5, right? So with 1 plus J 0.5, we could represent this as a phasor, right? If I'm just going to guess numbers, 1 and 1 is like 1.2 with an angle of 30 degrees, right? Something like this, okay? So it actually might be less than 0.2, right? So either way, we can always represent them as a phasor, which is kind of what they want to do. They want to represent in polar form, right? One thing they did do to save ink, they want to represent K0 as K times Z1 over P1. And so that all got crunched into this K value right here, okay? But it's still there, so remember that, right? Your first zero, you're going to take your magnitude of the phase angle. Your second pole, or your first pole, you're going to have a magnitude and a phase angle. And in your second pole, you're going to have a magnitude as a phase angle as well. So every imaginary pair is every 1 plus JW or Z1, every 1 plus JW or P1, every W in the circuit is going to have its own individual set of a magnitude and a phase angle. Okay. Now, with that, notice that this top one, the magnitude goes right here. Phase angle comes out right there. Okay. So that's accounted for. Everything else in the denominator, the W magnitude goes right here. And the 90 degrees goes right here. But notice negative. The reason why it's negative is because it's underneath the division sign. Anything underneath the division sign will have a negative angle every time, right? That's just basic phase arithmetic from the beginning of the semester, all right? And then lastly, for the pole, again, the magnitude will be accounted for right here, and the phase angle will be right here with the negative because we're in the denominator, okay? So in the end of the day, we got a magnitude, which we could number crunch, and a phase angle, right? And so our resulting output for a circuit will have a magnitude function and a phase angle function as well. Okay, well, this is your phase and this is your magnitude. Okay. Everybody follow me so far? You got any questions? Let me know. Okay. All right. So now, and oh yeah, we need to represent. How do you figure out this phase angle up here? How do you figure out this phase angle up there, right? That's what they're talking about down here. Well, let me do it real quick. Let's look at this one first, right? Well, let's draw, you know, every time we do a phase angle, I always draw an XY graph. So this is your real part. This is your imaginary, right? Well, real is a 1, so we're going out with a factor of 1. Imaginary is JWZ, so we're going up W over Z, right? So again, let's just do this. Figure out this phase angle. How do you figure out a phase angle? Tangent inverse, right? Tangent inverse. Right. How do you tangent inverse? You guys remember? It's always imaginary over real. I am over real. In our case, imaginary number is W over Z, so it's tangent inverse of W over Z. The 1 is there, so you don't, you know, you can just cancel the 1 out. Okay? And that's what they have right here. Okay, so I just want to explain, where does tangent inverse WZ come from? It's just your basic polar calculations. Same thing for beta, right? Right here, except we're using the 1 plus JWP. Okay. Now, so there's 2 major sections we have to look at. We got to look at the magnitude. We got to look at the phase angle. Okay. Typically, the magnitude is the most important part because that will tell you the voltage difference. Phase angle is just a time delay, right? So if you have a 90-degree phase shift, you could convert that to time shift, depending on how fast your frequency is, right? So a 90-degree phase shift means whatever comes out is going to be delayed by a certain time period versus what comes in. Now, if you're specifically on one channel, it doesn't really matter too much. For example, let's say we're on a phone. If we have a 5 millisecond delay in talking, does that really matter? Well, if I talk and there's a 5 millisecond for you to listen, you know, we can live with that. That's fine, right? Because we're typically not talking at the same time. I talk, and you talk, and I talk, and you talk. So this 90-degree phase shift, let's say, it's not that big of a deal. It's 5 milliseconds, right? But what if we had a parallel system, right? Let's say if everybody ever had to do Twitch recording or any type of audio recording and production, you have to deal with this your entire time, and I hate it, but you have to do it. You record, right? You record video and audio, right? Video processing goes straight through, right? No delay to YouTube, okay? Goes through a capture card. Audio, you have to go through my microphone, which I'm doing right now, right? But what if there's a 5 millisecond delay? So what's going to happen over here is you're going to be late 5 milliseconds. And you know what's going to happen, right? Your mouth is going to move at a different rate than what you talk. And that's incredibly annoying. I'm sure you've seen it before, right? Where you know, the audio is not in sync with the person moving his mouth, and it infuriates you, right? Or, you know, I've seen really crazy ones where, you know, I wish I had my video on, but I don't. To where, if you remember the old Chinese videos, the Chinese Kung Fu videos, where the person goes, you know, blah, 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 talking with his mouth, and then stops, and then the English translation comes out like 5 seconds later. I'm just like, what? Right? You know, that doesn't make any sense, right? So basically, anytime you have parallel systems like video and audio, you have to synchronize. So we have to synchronize these, right? And that's where, you know, a lot of filters and everything else comes in, okay? So in this case, phase angle matters a lot because you need to make sure the phase angle shift is not enough. If it's too much, we're going to notice. So we need to make a very tight phase shift for audio in this case. Or we have to introduce a 5 millisecond delay right here. One of those two, right? You have to sync up your audio and video, right? I used to download a bunch of movies from torrents and Pirate Bay, and the crap, you know, all the crappy ones always have this issue, and you'd have to go in VLC and artificially fix it. It was terrible, right? So again, this is where phase shift matters. But if you don't have the video and you're just listening to audio, then no one cares about the phase shift, to be honest. Okay. Okay. But this is the most important one by far, the magnitude. Okay. So we're okay so far, all right? So now we're going to go ahead and take that function and let's dice it up. Remember, there's 4 things. Let's go back up. There's 4 things in here, right? Or 3 things, sorry. We got our 4 things. We got our constant right here. So that's one factor we have to look at. We have a 0 up top. We have a pole on the bottom. And we have a second pole on the bottom. So there's 4 different quantities we have to look at. And again, if we could split these up into individual things added together instead of multiplying all together, we can bite-size piece this together a lot easier. And that's exactly what we're going to do. We're going to take a page off our old school Alexander Graham Bells and use our dB function. So let's take our magnitude or our gain or transfer function we already have, do the log 20 log 10 to get the gain in dB, okay? So literally you're taking the function 20 log 10 and then multiplying it into, again, K0, right? Which when you do your multiplication, it's gonna be right here, 20 log K0. Okay. Then we're gonna have our pole, or 0, right here. This 0 is gonna be split up with additions. We're going to have 20 log 10 of 1 plus JW over Z1. That's your 0. Then you're going to have your W pole right here. That's going to be negative 20 log W. Remember negative because we're in the division, right? If you remember log, anything on the top is going to be added. Anything on the bottom is going to be subtracted out. So this will be positive X, positive Y, minus Z, minus A. Okay, this is one of your log properties. And lastly, we have our second pole that we're going to have right here. Okay. So note we split out the function in individual things, right, for them. 20 log K0, 20 log of one of the Z1, negative 20 log of W, and negative 20 log of the pole. Okay. Any questions so far? I mean, this is the most critical part. Because then what we're going to do is we're going to analyze each one individually. All right. Okay. So now remember, we want to make a graph out of all this. So ideally, sorry, let's go back here. I want to figure out what's the graph for this one. Maybe this one's a flat line. Maybe this one does this. Maybe this one does that. And maybe this one does this. If we could figure out each one individually, we could then add all the graphs together and get a combined, you know, maybe if we add all these together, you know, we might just do this, right? This might be our graph. I don't know, okay? But that's the idea that we're trying to do, right? Trying to multiply 4 graphs together gets insanely hard. And that's what convolution is, honestly, is multiplying graphs, right? And we want to stay away from that as much as possible, okay? So the first thing we need to look at, and I'm going to go a little more slow here, is 20 log base 10 of K. Now, how does this operate? Well, first off, in the end of the day, remember, we're looking for this. We're looking for a graph based on frequency versus ADB. Okay. Now, one thing we're going to do, this is very important, is we're going to use a log scale on the bottom. Okay, what a log scale is, if you have never heard it before, is typically a normal scale. You go 1, 2, 3, 4. Okay, but because we're using a log function to begin with, the number is going to get very skewed out. So typically, when you're using a log function, you use a log scale. Okay. A log scale is you start with the number 1, and then every hatch mark is 10 times more. You get 10, 100, 1,000, and 10K. Okay. The reason why we like log scale is we can choose anywhere on this area and zero in on it. For example, you know, let's say I care about more what happens between 1 and 100. Because the graph between 1 and 10 is large, I can see all the intricate waves of the function. Versus if I wanted something between 1,000 and 10K, it's all crumbled up, so it might just do this, and we won't be able to see the details here. Okay, so it's nice at a log scale at lower frequencies, it gets expanded out. Because if this is a normal time domain graph, if you want to fit 1 to 1,000, I mean, you literally do 1 right here and 10K right here, right? And then if you just in the middle, it'll be 5K. And then right here will be 1K, right? So 1 to 10 might be like right in this little area. It's going to be, the function will be so small, it's just going to look like that, and you have no information, okay? So log scales tend to zoom in on lower areas, lower frequency where you want it to, right? One other big factor is, you know, you could choose where the log scale starts, right? It'll never start at 0. Right? Because 0 is undefined for log. So if I want to zoom in on very low frequencies, let's say I want to zoom in at 0.01 radians a second, right? Well, let's say, okay, in the middle of the graph, I'm going to put 0.01. Well, a decade before, it's going to be 0.001, and this one right here will be 0.0001. And then one more over will be 0.1, and this will be 1. Okay? Most of the action is going to happen around right here, so we scaled it in, right? Let's say we want to go very high frequency, right? I don't care about this minute scale right here. Well, let's say we want to do it in the megahertz range, okay? Well, let's put 1 megahertz right here, or 1, yeah, let's use the hertz. 1 scale below is going to be 100K hertz. Then a 1 before will be 10K. And then a 1 above will be 100 megahertz, or 10 megahertz, and then 100 megahertz, right? Again, because we want to see everything in megahertz range, most of the action is going to be right here, and we're not wasting any graph space on low frequencies. Like right here inside, Yeah, I don't care about what happens at 1 hertz and 100 hertz. That's outside the range I care about. So by using a log scale, we're shifting all the action to the area we want. In this case, 100 megahertz. Okay, so that's kind of why we're using a log scale. It lets us magnify what area of the information we want and what areas we don't care. Okay, so does everybody understand log scale? Okay, and you could draw as far as you want, right? I mean, eventually, you know, at some point you don't have to do anymore because you don't care about that area to frequency band, right? That's for the y-axis. On the x-axis, we're going to keep our normal linear scale of 20, 40, and 60. Okay, and we're going to have -20 and -40 as well. Okay, so this is called semi-log because we're half logging. We're logging on the x-axis, but we're not logging on the y-axis. Okay, so it's semi-log. Okay, so I assume probably most people would never heard of log paper before. That's why I want to spend about 10 minutes or so talking about it. Okay, so you got any questions, let me know, right? So going back to what we're talking about, you get 20 log base 10 of K0. Well, our graph is going to look like this. And let's say I want to zoom in at 10. So let's do 10 here. We're going to do 1 right here. We're going to do 100 right here. And 1,000 right here. And 10K. Okay, and this is W. And this would be our gain for this particular one. 20, 40, 60. Okay. Well, first question is, this is a constant, right? Does this change based on W equals 1 or 100? If it's a constant, it doesn't. So whatever number you figure out here is going to be the same for the whole entire graph. It's going to be a flat line, right? We just got to figure out, well, you know, let's say, let me use a different color. Let's say we got 20 log 10 of, I don't know, 150. Right? Well, what's that going to be? Well, 150 is not an easy number. We got to look it up. So open every calculator, 10 times second log base 10 of 150. I got 43.5 dB. Okay. So what you would do is you would figure where's 43. So that's about right here. And you draw a flat line. And this is 20 log 10 of 150. If you want to realize it's equal to 43.5 dB. Okay. So that's how you do a constant number. Now, what happens if, so question is, if K0 is greater than 0, we're going to be in a positive half, right? We're going to have a positive dB. Okay. What if K0 is less than 0? What's going to happen, right? What if this is 0.15? Right? Well, you got to do our numbers again. I'll tell you it's going to be a negative number for sure, though. Right? This, in our case now, this is negative 16.5 dB. So anytime your K0 is a decimal place, you're going to have a negative dB. Okay. No, it's K0. It's right here. Right? Because remember, K0 is a constant times any Z poles divided by any P poles. Right? You got to look at this one, not just the K value itself. Okay. Oh, hopefully that makes sense. All right. What happens if K value? What if K equals? What happens? So I'm sorry. You're right. I see what you're saying. It's not 0. I'm derping out. It's 1. Yeah. Good call. All right. What happens if K? So yeah, this is a decimal place like 0.1, and this is 10. Yeah. What if K is equal to 1? What happens there? K 0. All right. Again, you got to plug in a 1 right here. Oops. What's that going to be? Well, that's easy. Log base 10 of 1 is 0. So all this is 0 dB, right? So basically, anytime you have a graph on the positive side of the dB scale, you're increasing the gain. Anytime, so increase gain. If you're on the negative side, you decrease gain. And if you're on the axis itself, like this, no gain. You're keeping the same level. Okay. So we're pretty much out of time. I just want to start this real quick just to get people an idea of the poles and zeros. We did one of them. Next time we're going to come back and we're going to do the rest of them, and we're going to show you how to graph it all together. Okay, and if we have time, we're going to look at the phase plot as well. Okay, but again, this is all in the very back of the book, Appendix E and D and E. D is for decibels and E is for the Bode plots. Okay, so if you guys got any other questions, let me know. Otherwise, we're going to call it a day. All right. Honestly, I have to go pretty quick because I have a class literally at 1:30, so I need to immediately swap over and go to that one. Okay. So, all right, guys. It was fun. We'll catch you on Thursday. All right. See you later.